Okay, welcome to another of our Ken seminar series today. We have Kazmee speaking today on characterization of railroad ballast behavior under repeated loading using the large-scale triaxial that's located next door in the MPF, so you should take a look afterwards or sometime while you're up here to check it out. Hassan's been here. What year did you come here? I didn't see that.
Fall 2010.
Fall 2010, so a very short amount of time. You have a ways to go, right? That's a joke. He came from Oklahoma State?
No,
University of Oklahoma. Oops.
Sooners.
Sooners, yeah. With the Masters, and then he got his Masters in Bangladesh. So let's welcome Hassan to the talk today.
Welcome to our Kent weekly seminar, and today my topic is characterization of railroad ballast behavior under repeated load using a new large triaxial test setup. Before beginning this presentation, I would especially like to thank Dave and James for their ceaseless help in this project. I would also like to thank Professor Errol Chutumluar for letting me work in this project, as well as I would like to thank David Reed and Eric Geringer for supplying the materials that we have tested with this new test setup. So here is my presentation outline. First, I will discuss about the University of Illinois triaxial ballast tester that is popularly known as TX24. Then we will go for the specimen preparation and the test procedures, how we are compacting the ballast samples, how we are testing, what kind of load shape that we are using. Then I will be discussing the repeated load triaxial test results. Some of the main features that I will be discussing is effect of a stress ratio on permanent deformation, followed by effect of rest period on permanent deformation of the railroad ballast, and then effect of Geogrid reinforcement on permanent deformation. Also, we will be presenting results about different ballast types and field degradation trends on permanent deformation accumulation, as well as I will be presenting shear strength test results on a specific type of ballast material, large limestone ballast material. So as you can see in the picture here, this is our TX24 setup. It is displacement control stress strain testing setup. It can also be done. It can also do load control repeated load testing. The MTS actuator that we have is capable of applying 22 kips of dynamic loading, and it has a load cell of 20 kip capacity, and then the whole test setup has 3 axial LVDTs to come up with the vertical deflection that is being experienced by the specimen, and the range is plus or minus 25 millimeter. We also have a circumferential LVDT to come up with the strain, volumetric strain, the change in the specimen diameter. Setup for the sample preparation. Compaction setup. First, we install the base plate, and you can see there are 2 ports for vacuum application or the pressure application. We usually use 3 latex membranes to compact the specimen. First of all, we wrap around the mold 2 inner membranes during compaction, and after compacting the specimen, we install another outer seamless membrane for vacuum application, and the total membrane thickness is equal to 2.3 millimeter. For controlling the ballast fines that can pass through the vacuum lines, we are also installing the geotextile at the very bottom of the mold. And this is the whole setup, split mold setup that you can see here, installed with the vacuum pump. This is the electric jackhammer that we use for specimen compaction, a 65-pound jackhammer. And we use a walk behind forklift to lift that jackhammer and then put it down and then press the button to compact the ballast layers. Specimen compaction in layers, we do it in 4 layers. Each compaction each compaction of layer consists of 4 seconds of pulsing with that jackhammer. And after compacting each layer, we also check the specimen height. Also, the top of the specimen, when we are finished with compacting the whole specimen, the 24-inch specimen or 300 millimeter specimen, we also check the top of the specimen for level. And after that, we instrument the specimen with the axial LVDTs that we have here on a 10.5 inch span, and also the radial LVDT that you can see here to come up with the circumferential deformation. That is the load cell model that we have here, Honeywell model 3174. And as you can see clearly, these are the 3 LVDTs that are installed 120-degree apart, and 1 radial LVDT or circumferential LVDT mounted around the specimen. And this is the instrumentation phase. From the load cell, it connects up to the top of the chamber, acrylic chamber, and from that acrylic chamber, it is connected to the MTS controller as well as the transducer indicator, and those 2 stations are also connected to the computer. We collect the voltages and then we convert the voltages into the into our raw data. To check the vacuum pressure, I mean whatever pressure that we are intending to use during the whole testing, like shear strength test or repeated load testing, we can also keep an eye on the pressure level with the vacuum that is installed at the base plate, with the pressure gauge that is installed at the base plate. And this is how the screenshot of LabVIEW program looks like. The axial LVDT readings and the radial LVDT readings, how much load you are pulsing. You can also check it in the graph here. We have tested 6 different ballast materials. Type 6 is the ballast materials that have been generally used for repeatability of results, test results. And if you go back at the back side of the MPF, you can see a pile of limestone. That's basically the type 6 ballast. And from the UP box test study, we have got 5 different materials. Those are the 5 different materials that you can see the gradation, and seeing the gradation, you can check that type 5 has the finest gradation and type 6 has the coarsest gradation. Yeah, I have already discussed that type 6 is the limestone ballast, matching the ARIMA number 24 gradation band. And we have also checked that whether the compaction alters the gradation. This was done on UP ballast boxes test study at 234 MGT, and for 5 different materials, we didn't see any, large amount of change in the gradation. Different compaction durations were also tried, but we finally stuck up to the 4 second per layer compaction, because that way we were being able to not altering the gradation characteristics. These are the gradation chart that you can see with respect to the sieve sizes and the 5 different materials. And you see that if you see at number 200 sieve, that means 0.075 millimeter sieve, there is not that much change between before compaction and after compaction specimens. And here is the fouling index that we have of those 5 materials that we have received from UP ballast box test study. Now I will be moving to the repeated load triaxial testing, assessment of permanent deformation. This is a picture from our recent FRA study where you can see the loading wheel loads, actual wheel loads that is being happened on a Amtrak track line, and you can see the load that is experienced by the strain gauges as well as the deflection by the multi-depth deflectometer. So you can see the load pulses. So with the triaxial test setup that we have built up, we are also trying to simulate this type of loading. So that's why we are using 2 different stress ratios, one with 4 and one with 6, and with different confining pressure and deviator stresses. Also, we are simulating the Harvesine pulse shape loads by applying 400 millisecond, that means 0.4 second of pulse duration, load pulse duration, and 600 milliseconds, that means 0.6 second of rest period. And we are doing the test, repeated load triaxial test with 10,000 load applications on those 5 different ballast materials. And these are some of the pictures, these are some of the graphs that you can see. The response that I have showed from the actual field work also simulates from our ballast testing, that Harvesine shaped load that we are trying to simulate in the lab.
Hassan,
Yep.
can you please define what a stress ratio is, and also
A stress ratio, by a stress ratio I am meaning that the amount of stress that you are applying, that means the deviator stress sigma d plus sigma s, that will give you the sigma 1, and the sigma s equal to the sigma 3, that will give you the confining stress. The stress ratio is basically the ratio between sigma 1 and sigma 3. And the importance of on-specimen instrumentation. Many of you may wonder why we are installing 3 different LVDTs instead of just depending on the LVDT that is inbuilt in the actuator. Here is the reason. If you look at this graph and check the permanent deformation, then you can see that the actuator that you have, the actuator test results of permanent deformation is based on the deformation on the whole specimen, just based on the reading on top of the specimen. On the other hand, the 3 LVDTs that we have, they are moving with the specimen and along 3 directions. So instead of just depending on top of the specimen, when you have 3 different radial LVDTs sticking up to the sides of the specimen and moving along with the specimen, and you can better capture the permanent deformation trends or the permanent strain trend that you are seeing here. And we have often noticed that between these 3 LVDTs, among these 3 LVDTs, 2 of the LVDTs are generally close to each other and 1 is not. That's the general case. So your specimen may be tilted and you may be getting wrong answers if you are relying only on the actuator displacement for the permanent deformation trend or the permanent strain trend. Here we can show you the effect of stress ratio. We have tested the limestone materials with two different stress ratios, stress ratio 4 and 6. When you increase the stress ratio from 4 to 6, there is a significant increase in the axial deformation. Axial deformation means permanent deformation plus the recoverable deformation. So it is also true in case of the permanent deformation. Permanent deformation is nothing but the lower end of these curves. Okay? And if you check that the stress ratio, when you are increasing the stress ratio, your axial deformation, permanent deformation increases significantly. Effect of rest period. As we have told that with the ballast triaxial test setup, we are trying to simulate different types of loading that is being experienced by the railroad ballast, which is which have been being used in different track lines. So here you can see that if we can allow the rest period, the material can relax and get the recoverable deformation, get back to that portion, and just sustain the permanent deformation. On the other hand, if we are not allowing the rest period, it is a continuous loading like 0.4 second of loading, then you will have this permanent deformation. So if you compare these two lines, you can see that without the rest period, the permanent deformation is quite high compared to the with rest period permanent deformation trend. This was also done with the limestone type 6 ballast. We have also tested the permanent deformation trends of type 6 ballast with Geogrid, and we use Triaxial Geogrid that looks like this. And we have set up one Geogrid at mid height and two Geogrids at 1/3 heights. And these are the Geogrid results. If you look at the stress ratios, for stress ratio 4, you have the lowest axial deformation, but when you increase the stress ratios up to 6, you have significant amount of deformation. And as you can see, if you install the Geogrids, your permanent deformation gets down. So advantages of Geogrid reinforcement clearly apparent. Effects of a stress ratio appear to be more significant than Geogrid.
Can you explain that? I don't quite see what you mean. Where's the benefit? I don't see that.
in the black and the red one on the top, and between the brown or whatever color and the blue one at the bottom.
Yeah, but if you put two Geogrids, it's worse. So
Yeah,
how does
so
that make any
there is a
sense?
reason for that.
Yeah, I will be explaining it later on. This is the Union Pacific ballast box study. We are investigating the effects of ballast material types and degradation trends on modulus and permanent deformation. We have tested 5 different ballast types, namely type 1 to type 5. These ballast materials were collected from track 2 of South Morrill UP subdivision, Ogallala, Nebraska. Ballast type 1 was 1 to 4 was clean ballast. Ballast type was 5 was same as type 2 but not sieved. And on that track line, we generally have 250 mgt of core traffic annually. Ballast sampled twice yearly to monitor the degradation. On May 2011, November 2011, and May 2012, they have given us 3 different samples of materials. We tested the first one and we didn't get good results because at that time we have some issues with the signal that we are getting from the LabVIEW program. We corrected it and then we came up with the results here, as you can see, type 5, among those 5 gradations, type 5 had the highest amount of highest amount of fouling index. That's why type 5 had the highest permanent deformation, followed by the type 3, then type 4, then type 1, and type 2 had the lowest permanent deformation. But right after 6 months, here is the correlation between the fouling index and the permanent deformation. We didn't find any direct correlation between the resilient modulus and the permanent deformation or the fouling index strengths, but we definitely got something in between fouling index and the permanent deformation. The one material that we have, type 5 control ballast, it had the highest amount of fouling index and it showed the highest amount of permanent deformation. But 6 months later, TTCI provided us with again 5 different test materials after 320 mgt. Maybe it's a sampling error, but it had percent passing 12.5 millimeter. Based on the percent passing 12.5 millimeter, type 4 was greater than type 5 and greater than type 2, and after 12 months type 3 showed higher fouling after 12 months than after 18 months. And these are the results that we have got, and according to that results, after 18 months of service on the track line, type 2 had the highest permanent deformation and type 1 had the lowest permanent deformation. But 6 months earlier, type 2 showed the lowest amount of permanent deformation. So that may be a sampling error, but we tried to analyze the results in terms of meal abrasion ratio. So that's what you can see. Meal abrasion ratio gives you the degradation term of those particular ballast materials, and if you look at those meals abrasion value, you can see that type 2 had the highest meal abrasion value and also the highest amount of permanent deformation trend after 10,000 cycles. So the conclusions here are type 2 showed the highest meal abrasion value, no correlation between MR and permanent deformation. Ballast fouling, both ballast fouling and ballast toughness can contribute to the accumulation of permanent deformation. So far the findings from the repeated load Triaxial test is that it is capable of simulating realistic loading conditions experienced by the ballast layers under train loading. Selected specimen compaction procedure did not lead to significant particle breakage. Effect of stress ratio was found to be more significant than the effect of geogrid reinforcement. And continued testing of UP ballast Boss test study ballast may lead to definite correlations between particle degradation and permanent deformation accumulation. Now I will be discussing the shear strength test on geogrid reinforced specimens. These specimens were constructed with the type 6 limestone ballast materials, and these are the positions or the locations of the geogrids that we have tested within the specimen. We have placed we have tested 3 specimens with 1 geogrid, one at the 150 millimeter from the top, one 150 millimeter from the bottom, and another one right at the middle. Then we have also tested 2 specimens with 2 different geogrid locations. One is from 150 millimeter from top and bottom, and another is 250 millimeter from top and bottom. And the confining stress was sigma 3 at 138 kilopascal, that means 20 psi. We have used 2 different types of Triax geogrids. One is the Triax one, and another one is the European KSS geogrid. So this is the peak deviator stress that we have found in the lab, and as you can see, with the peak deviator space right at the, for the specimen with Geogrid at the mid depth of the specimen, Triaxial and European SS almost had similar kind of shear strength test results. That was also true in case of Geogrid placed 150 millimeter from bottom, that means 6 inch from bottom of the specimen. Similar trend was also found in case of the 150 millimeter from top of the specimen. And among these 3 specimens with only one Geogrid, you can see that the one that is 150 millimeter from top of the specimen had comparatively lower strength compared to the other 2 one Geogrid specimens. And here is the test result for peak deviator stress and Geogrid placed at 150 millimeter from top and bottom of the specimen. And surprisingly, as you can see, that the shear strength that was exhibited by the 2 specimens, the Triaxial specimens and the European SS specimens, were the lowest compared to the compared to the one Geogrid specimens. And if you look at the other side, 2 Geogrids placed at 250 millimeter from top and bottom of the specimen, you can see there is a significant increase in the shear strength compared to the one Geogrid specimens. So based on the location of the Geogrid placement, Triaxial and European Geogrid specimens exhibited different strength. Specimens with 2 Geogrid exhibited highest peak deviator space among all the specimens. But what's the reason? And this is actually the cumulative picture of all the trends that we have found from the shear strength. And you can see a lot of jumps in these curves, shear strength curves. These are not smooth. You may wonder why. So here is our answer. One by one, when these Geogrid ribs are being torn apart, I think they are making these shifts in these curves. These jumps was because of the breaking of the membranes and continuous reorientation of the ballast materials that we are experiencing in the whole specimen. So that's maybe the reason we didn't have any smooth curve like in case of soil that we are expected to see. These are the percentage change in peak deviator stress, and you can see that 150 millimeter from top and bottom had very small amount of gain. In fact, in case of European SS Geogrid, it performed worse even with no Geogrid materials. So what's the reason? Effectiveness of Geogrid depends on the assessment of failure plane. If you are placing your Geogrid along the shear plane, then you will be getting the benefits, otherwise you will not get the benefits. So from the test results, we can see that if you put two Geogrids, but that does not capture the shear plane, you will not get the result that you are expecting to see. That's what I have written here. The shear plane is not seized if the Geogrid is placed at 150 millimeter, either from top or bottom or both. Double layered Geogrids across the shear plane can significantly increase the shear strength of the corresponding ballast material. So that's all I have so far right now. I would like to acknowledge some of the input from BNSF Railway, TTCI, also from our group Anthony Moreno, Daryl Marrow, Tim Punkard, Mark Gillen, Michael Bladesinger, Carlton Ho, Illinois Center for Transportation. And thank you.
Questions for Hassan?
Question. So you talked about the stress values that you chose for your deviatory stress and all that.
Yes.
So how did you arrive at these values? Because on
We
the
have
train track you have measured the load, not the stresses. So did you calculate the stresses at that level? Or how?
No, we didn't calculate those loads from the actual field test data. What we did some literature review, and from that literature review, what other researchers have used, what type of stress ratios they have used, what type of confinement that they have used, and what type of confinement that we are comfortable with our test setup.
How do you ensure that the stress values you have chosen corresponds to the grid condition?
It is solely based on the literature review that we have. We are now looking at the real life test data, and then we'll be coming up with the test specifications that we need to follow. But whatever test values that, whatever confinement and whatever deviatory stress that we have used, it is solely based on the literature review.
Well, we did look at literature review a lot, but there's also sort of requirements on how you design that. Typical stresses that you design for railroad track or ballast layer. Ballast layer is not something that you change the thickness design. It comes standard, about 12 inch under the concrete tie and 13 thickness for the wood tie, whatever. But for the stresses, you're not supposed to exceed some 25 psi, 50 psi, that would mean like the subway stress is different. So there's no way to really measure the lateral pressures in the ballast because of the large size of what you feel comfortable as low confining pressure is what people have been working on. Basically, are fine. So higher the confining pressure, obviously higher the resistance to carbon deformation. Usually going to a lower value is more critical for you. And actually, there's an expedited way, showing you the potential of the materials because more tendency to bulge. This is all about that bulging, actually. A couple other points that he was talking. I'd like to make some additional, providing some additional information. I fully support what he said from the point of Geogrid is not cutting the shear plane, for example. You're not getting and seeing any benefit. And especially if you're putting close to each other, right in the middle, those two grids. That's where all the bulging and the movement is, and grids are very good at arresting and holding. That's how it's working. If there's no bulging towards the both upper and lower ends of the specimen, you don't see the benefit, and that's what he was trying to show. One other point is that in the TPCI study, those 5 types of materials we kept receiving from their major Western megasite location where the ballast box tests were going on, 5 different ballast materials, types 1 to 5. They kept sending us every 6 months those ballast materials in limited quantities, sampled from different parts of that same ballast box of the same material, ballast material used. And they always came to us with a different, probably, percent fouling content than what was separately reported found in just the degradation study on site. So there may be some mismatch that we found that is actually not helping us explain some of the results. So we need to do much better job in terms of the sampling and knowing exactly what we receive and what's the gradation on that, how that relates to what they found as for those gradation. Increasing the amount of funds. So,
all right.
Yeah, sure.
Is compaction you did with some kind of, is it like a dynamic falling wet kind of?
No.
Or is it vibratory?
Vibratory.
So,
You have that video?
Yeah.
compaction has to do a lot with your permanent deformation behavior. So
That shows the whole procedure, but during the compaction, I will slow down. James was really fast. That's how we are compacting.
how does it again correspond to
there any way to
assess that it corresponds to the field compaction?
By field compaction, field is quite different. I mean, in the field we do.
Permanent deformation results are going to be different than what we observe in the field, unless there is some kind of
Correspondence between these two.
Yeah, yeah, sure.
So the funny part about ballast construction is that there is no density check or anything in the field.
Yeah.
Okay.
There is no way you can
so
check
you
the
just lay the ballast and then they just bring something called drag stabilizer. They just vibrate it and whatever it is, it is. There is no way because I mean you can't use a nuclear gauge of course to test that and then again it's a large topic. People are working how to study that. So that's the first point. So Professor Tumler's one of the students, Hai Huang, who is now a professor at one of the Penn State universities, when he was doing his PhD and they were working on a lot of discrete element work, that is when some of those UP ballast box studies started, and what they tried to achieve is at least how do you simulate the field conditions in the DEM. So they started to correlate that to void ratio. So just measure how much material is going in a given volume and then correspond. So that void ratio they found to be about 0.6 and in that range. So when we constructed these specimens, the first idea was to somehow keep the void ratio around the same. So yes, there is a lot of, definitely there is a lot of, what do you call it, variability still associated with it, but these guys have, like we have prepared so many samples, they know that, okay, if you put about 150 pounds of material and then, what he just said in actually 5 seconds about how they compacted every layer for 4 seconds is actually a study that took them about 2 weeks because we didn't know how much vibrating effort it will take.
So we are applying different durations of
you at 4 seconds, 6 seconds,
compaction.
6 seconds and check the degradation and then come out with that. So basically it's kind of matching the void ratio.
Okay, Aaron?
I guess my question somewhat overlapped with that because you said you compacted in 4 lifts, and then that seemed to actually dictate the spacing of your geogrids in a lot of situations.
No.
Right.
Okay, and I guess it becomes a threefold question then. Why do you select 4 lifts as opposed to the more conventionally accepted 5 lifts that are used for smaller diameter triaxial specimens? Are you able to still achieve your target, whether it's target density or a target void ratio, as Deb was hinting at? And because of using 4 lifts rather than 5, did you actually notice increased degradation of the material?
No, we have already shown the results that within the gradations, between the gradations that was done from before compaction and after compaction, there was no change in the, appreciable change in the gradation characteristics. We are basically using 4 lifts to match up with the void ratio concept, but density is a long shot, I think, in case of ballast, but because we don't know, I mean, what will be the density of that particular ballast material? Can we even match with respect to the track line density that we are having?
Let's say your 4-second compaction was dictated by your 4 lifts. So if you went with again the more conventionally accepted 5 lifts, would you be closer to the?
Well, we are not dealing with the highway materials. We are not dealing with the highway materials. Yeah, go ahead.
Aaron, the funny thing about ballast is that if you're just finally packed those large particles in some configuration, unless you just have to make them move to sideways or whatever, if you continue to vibrate, if you're not crashing and you're not supposed to crash, additional seconds will not get you anything. So that's how we started with the large shear box in the basement of New Market, and that's when we realized that after a certain type of settlement and compaction, you cannot improve more on top, and that's where you stop. So in a way, we cannot shoot for a density, but depending on the angularity and the packing of the rocks, we finally get a density.
One more thing to answer your question about the geogrid placement. So how that was done is, for example, in the geogrid at mid height, which is at 12 inches. So what they did, I think, is they first prepared an 8-inch layer, compacted that, then hand placed 4 inches of material, placed the geogrid on top of that, hand placed 4 inches of material, then compacted the whole thing. Because it's critical not to compact and then place the geogrid and then compact, because you need to have some loose material underneath also for the geogrid to penetrate into the material.
And
So
you will have that aggregate interlock that you are trying to
hand
achieve.
placed and then compact.
You don't think this material is naturally scarifying between layers? I mean, would it actually drastically affect your results if you did compact that 4 inches, then place your geogrid, then compact another 4 inches? Would that be significantly different than loosely placing, sandwiching the geogrid, and compacting the entire?
Yes, yes. We have done that test and we had some weird results. So that's why we had to.
Weird, what does it mean weird? Like lower?
Yeah.
Show those data.
And another addendum is that during one of the compactions, one of the research collaborators from one of the Geogrid companies, he was actually visiting, so he was actually saying that you should probably hand place some material, and then this guy is an academic guy who did a lot of research, so we just followed.
Yeah, although we saw the aspect here being an effect, I mean having an effect. When you go back to more dense graded materials like either base course material or soils or whatever, placing any kind of a geogrid on a compacted smooth surface like that, now with higher fines, you cannot establish that aggregate interlock. And if you can't, then it's just providing you a shear layer, but nothing reinforced by interlocking of the aggregates and the
Right, you don't seem to have a lot of fines in this material, and I guess the concern comes from when he shows the curves, what initially appeared as noise, but he described as the breaking of the individual strands of these geogrids.
As well as particle reorientation that is going on
Sure.
around those broken ribs.
So do you not somewhat expedite that if you're loosely placing the geogrid and then compacting the entire layer? Are you somewhat pre-stressing these individual strands on the geogrid during the compaction process?
No.
Well, we have done that. Before doing the shear strength test, we have also checked what is the condition of the geogrids, whether it is affecting the geogrid while we are compacting. Okay, and we have taken it out. I don't know how has it been performing mechanically. Has it been mechanically strained? I don't know, but from visual checkup, I didn't see any. Significant change in the.
Do you have a bulge specimen picture to show? There's quite a bit of bulge, and that movement, that tendency of the aggregates to go lateral, that's pushing, or rather pulling, I should say, or pushing at the same time, individual ribs, and that's how we get the geogrid damage.
Let's, anybody else with a question? Yeah, Jaime.
The position of the geogrid in the layer, you mentioned that it should be in the bulging zone, right?
Yeah, bulging.
How is the boundary conditions in the test compared to the ones in the field affecting the location of the geogrid?
Well, that's a tricky question.
What do you think the answer is?
Would you please repeat your question again?
Like the location of the geogrid is in the bulging zone, right? But how different is that location of that zone in your testing in the lab when compared to the field? It's going to be the same, it's going to be different?
Just asking, is the place you put the geogrid in the field going to be a similar location than what you did over here in the lab? Would you put it right in the middle, or is it going to be in the upper third, or what? Is that your question?
Yes.
It has to do with end effects too, right?
Yes.
Good question. How do you get by the end effects? I mean, get rid of end effects in your specimen testing? Why don't you explain that first? End effects of the specimens, top and the bottom end?
Yeah. The top and the bottom, if you look at the whole specimen, the top and the bottom looks intact, while the sheared plane, you can clearly, in case of some of the specimens, you can see the clear shear plane as well as the bulging portion. So if you think about the shearing envelope that is being helped, that is being experienced by the ballast layers while the train is moving, like this and this. So you have to assess, I mean, where will be your, where can be your failure plane, okay? And
where do you get your deformation measurement? Let's say you're doing parallel deformation test with the geogrid placed in the middle. What's your dial gauge location?
right in the middle, 10.5 inch, the bulging
Middle
zone.
of the specimen, right?
Yeah.
So you're looking above and below the grid, basically. What's happening?
Yes. Yes.
The middle foot, is that what you're saying?
Yes. The middle.
But I think the other question that I don't know if you answered was, if you were going to put this in the field, where does it go? Does it go in the middle of the ballast section, the bottom, the top, or you don't know?
Well, I will suggest in the middle, as well as closer to the top, not at the very bottom.
Okay. I fully agree with those, actually. If you want to cut
Not
down
exactly on the
permanent-
top,
Right.
but a certain depth below the top,
Right.
as well as in the middle.
If you're intending to cut down permanent deformation within that layer, middle to higher, above that middle line is actually where the stresses are the highest that you want to. And the rule of thumb on that is that actually the bearing capacity failure lines, if you draw those within that layer, you don't want to be below that bearing capacity failure plane. You want to get that grid to reinforce that failure plane. That's what.
Any other questions? I'll get one.
Sure.
Well, what I learned from your presentation, which was good, was obviously these materials don't have much permanent deformation. Is that a true statement? I mean, in terms of percent strain, it's very small. That's what I got out of it. I mean, you were talking 1 or 2 millimeters over a fairly long gauge length.
Yes.
So in terms of permanent strain, these are extremely small. You agree with that?
Yeah, to some extent. I agree.
Okay. And then,
But if you increase the shear strength ratio, I mean, like, the stress ratio,
sure.
when you go up to 6, when your confinement is as low as 5 psi, you can see significant amount of straining.
Or at least in the data I saw, I didn't see.
Most of the tests that you have seen, the test results that you have seen, it's based on the 8 psi confinement.
Okay.
We haven't gone, I mean, there are very few results, like the, like, yeah, SR6 was, I think, 5 psi.
Yeah, I guess when
In
I-
case of 5 psi, you can see significant amount of permanent deformation. But if your confinement is that high, you will not, your specimen will not exhibit that amount of permanent
I guess one
deformation.
thing I learned, and I'm not sure I'm convinced by your arguments yet, that the Geogrid actually gives much benefit. I mean, the strain levels you're showing are so small, and then you do your permanent strain, you do your rapid shear test, and those are at 10 or 12% strain to get a result. So you're actually doing.
No, for the rapid shear test, I think it has gone.
At least that's what I saw. I thought I saw.
I think it's quite high.
Which fits in with what I'm thinking is Geogrids don't work that well at very low strain levels. They're not as effective. Yeah, you have.
Yeah, it has gone up to 16.
Yeah,
16%.
which means, but by the time you have 16% strain, your train probably isn't running on that.
Yeah.
So my point is that I'm not convinced by your data, and I could be wrong. I'm just, it seems like it's a little gray that I don't know why I would pay extra money to put in Geogrid. I'm not seeing the benefit here unless you have huge strain levels, and these are good aggregates. So why am I putting this in? This is just my comment. I don't know if there's an answer yet.
Well, these are fairly clean ballast. If we are using fouled ballast along with Geogrid, the test results may be different. So more research is needed.
Yeah, I would say clearly if you have a poor quality aggregate, I would probably agree with you. But in this case, why would you put a good aggregate with a Geogrid? Makes less sense to me.
Can you tell us what is the finding by other researchers in terms of using geogrids for other ballasts, so whether they have found it to be beneficial or not so beneficial?
Well, you can find results on both sides, I guess.
Which I would agree. I personally think based on the data you're showing, you seem to be
at least the data I saw, overselling the effect of geogrids. I mean, it's not that clear.
If you put a percentage, those lines will be right on top of each other. Do you agree?
Yeah.
Okay. Oh.
There goes your research sponsor.
Okay, you should have some stronger beliefs in what you're doing and explanations of what this test is all about and how it relates.
But we are testing with, clean ballast. We are not testing with.
You should always realize that what you're doing and running the test in the lab with only up to maybe 1,000 or 10,000 cycles is only the beginning and a little bit of what's happening out in the field. In the long run, when you have 90 MGT, this is million gross ton, okay, we were able to relate that. 600, 700, 800,000 load cycles as opposed to our at most 1,000, 1,000 load or 10,000 load cycles. A couple different mechanisms happen. Ballast aggregate materials crush like unbelievable, okay? And that never happens in highway base courses. Repeated load application. And that movement, strengthening and arresting the movement of ballast so that the ballast doesn't reorientate and break the flat elongated particles and everything stays, is exactly what geogrids is contributing in the long run to cut down the permanent deformation, which is not the mechanism until the last zigzag, whatever up-down cycles that you get. Because that's the type of deformation that in the field is supposed to be prevented by geogrid, and that's the long-term performance benefit. We don't obviously see that in the small test, small scale, small duration test.
Yes.
So that
The concept of incremental collapse or the shakedown concept, it is not captured within those 10,000 cycles.
In the lab with the same standard procedures to be able to rank with and without grid or wherever, but not exactly related to the life performance
Yes.
of that ballast layer for a 2-inch deformation settlement in the field.
Yes.
But you can relate the two, although they're not the same. So that should be your explanation.
Yeah, if I can, Professor Hessler, I can add one more thing.
30 seconds.
What's that?
30 seconds.
Okay. So what we are applying here is just a repeated pulsing load, but what the ballast layer in the field is going to see is all the vibrations coming from the train and everything. And we are just having a cylindrical sample in a membrane and confined, where in the ballast layer there is a lot of other room, like you vibrate, it's almost like something jackhammering the rail, and there is a lot of movement of the material that can actually migrate away from the ties, which people have seen. So that is when the geogrid comes into picture. At least it prevents the migration, which may not be reflected in a repeated load triaxial test, but the application really holds the material together, and then it improves its performance.
Oh, thank you. Next week we have
I'm presenting.
you can ask me tough questions.
Oh, you're